So let's as well start. And today we are actually going to start the deep dive into the neural networks, both the shallow and deep neural networks. And throughout the introductory lecture, I will talk a little bit about the history of the field and how it has been developing. And after that, we are going to go to the collab looking into the application of the neural networks for the real world problem. And in other words, why deep learning is actually pretty easy now. So let's start first with the little bit of history over the last 10 years. So as you can imagine, and this is the reason why all of you are interested in this course, neural networks and machine learning currently is pretty much everywhere. So in fact, the last decade have seen almost unprecedented growth of the interest and investment and number of people joining the field in deep learning. This started with the very famous paper by Sutskever in 2012 called the Deep Learning. And almost immediately, this work have stimulated the wave of interest from the industry and the scientific community. And after that, the new development were appearing almost, if not daily, but at least every several months. So just as a few notable milestones, 2014, so less than 10 years ago, in fact, saw the emergence of the generative adversarial neural networks and variational autoencoders. So some of the leaders in the field of the artificial intelligence refer to GANs as the invention of the decade. Turned out they were not exactly right, because after that, the inventions of the decade were appearing almost every year. So a big splash was the development of the AlphaGo, which was the first example of the computer playing computer games better than human. 2017 was a huge milestone of the development of the transformers architectures. So a very famous paper called "Attention is All You Need" basically heralded the introduction of this technology. And also it laid the foundation for the technologies that we deal with now. For example, ChatGPT is ultimately based on the transformers. So in 2018, the graph neural network started to become big. And there was also one small development, which, as far as I understand, originally was an experiment from Google, which is the development of the Google Colabs. So this technology, which is exceptionally convenient to use, is actually very, very recent. And it basically democratized the machine learning for everybody. So prior to the Google Colabs, you have to set your own environment. You need to figure out how to make your Python IDE to talk to the graphic cards if you want to use the GPU and so on. Once the Google Colab appear, the entry level to learning Python and actually experimenting with the deep learning dropped essentially to zeros. So 2020, 2021 was the mu0 and the AlphaFold. And of course, the things become really hectic over the last half a year with the techniques like Galactica from Meta, ChatGPT, and so on becoming out there on the market. So this is really a ride for the last 10 years. What is very interesting is that these developments span the areas of the classical computer science, from computer vision to medicine to autonomous system and games. But at least so far, the progress and impact to the experimental physical sciences have been relatively small. In fact, one of my colleagues, Ben Bleizik at Argonne, have analyzed the publication activity in the fields of material science, chemistry, physics, computer science, jointly with the artificial intelligence and machine learning. And the dynamics in this field is actually very interesting. So obviously, publication activity is not a very good measure of the effort, but at least it's a good proxy measure. At least it tells you how interested are people in some specific area. And what you can see is that in chemistry and computer science, there was a very healthy interest and growth in the number of publications using machine learning, starting from essentially before the year 2000. The addition of the deep learning resulted in the inflection point of this curve, so the growth of application become considerably faster. And of course, as you can expect, the computer science have adopted the deep learning faster than chemistry. But the important thing is that these fields have a history and tradition of using machine learning for the real world problems. The situation in physics and material science is totally different. So prior to about 2016, 2017, the number of publications is almost exactly zero. So in this case, we can say that there are, of course, few groups, my group including, that worked on the deep learning early on. So my group started to work on it around 2007. However, these were really small and niche activity, and in most cases, this exponential growth of the activity comes from the influx of the ideas from other fields. So from this perspective, whatever we do in application of machine learning in microscopy would be relatively new. Now, let's zoom out a little bit on history. So we looked at the development of the machine learning in over the last decade, and it is nothing sort of spectacular. The question that you may ask, how long is the history of the field? And this is actually the reason why a lot of people are very careful and cautious about machine learning, because the history of machine learning in the field started in around 50s, and then it went through the two periods of boom. So the good old-fashioned AI, the first one when the concept of the AI has been created and caused a very large enthusiasm. It was shown by several people that the modes of the AI that existed at that time cannot work for multiple classes of problem. And the first boom in AI have been followed by what is called the first AI winter. So there was a second AI boom somewhere between early 80s and 90s, with the concepts like knowledge engineering, the shallow networks, and so on and so forth. And this boom has been followed by the second AI winter. So the question becomes, we're clearly now in the time of the third AI boom. The question you may ask is whether this going to last, or whether we are looking at the third AI winter going forward. And before we go there, let's first look a little bit about what is the neural network in the first place. So how is it different from physical models? So generally, the artificial neural network, using the definitions that were created in the 50s, is basically a mathematical model which is essentially based on the biological neurons. So we have a group of neurons that process information using what is called the connectionist approach. So this is an old word for the neural network. And the model changes the structure in response to the information flow. And from certain perspectives, neural networks, all of them that are out there, are the universal interpolators. So all they try to learn how to do is to take the inputs and build the best relationship between the input and the output. This is it. So imagine that if we want to deal with some sort of the physical problem. So if we try to solve it through the classical approach, for example, the functional fits like Gerd have shown in his lectures, we actually need to know quite a lot about our problem. We need to have the domain knowledge. We know that the fits can be slow. Sometimes we know that they cannot be implemented in real time. And the physical approach is ideal if the physics of the problem is known. So if we know physics and our knowledge is solid, we actually should not be using neural networks. So neural networks is a little bit different. So in this case, we need to invest time in training. They work very fast. They can be implemented in real time, and then allow us to multiply to multiple similar tasks. So currently, if you go from the neural network to the deep neural networks, the difference is actually very simple. Deep neural networks have multiple layers. That's why they're deep. shallow networks have several layers. Practically, we started to have the capacity to develop deep networks only 10, 15 years ago. Before then, it was well outside of what you can do with the personal computer or the relatively small cluster. So once we have this concept of the universal interpolator, we can define several classes of tasks that the neural network can do. So the simplest task is so-called the supervised machine learning. So this is the case when we give the network the examples of some sort of system. For example, we can show the dog and the book and the network and give the examples of the labels for the dog and the book. And the neural network will learn to recognize them in the image. The unsupervised machine learning is when you present the network with the data, and then the network actually learns how to find the internal structure of the data. Semi-supervised machine learning is the hybrid between the two, when we have the only partially known labels. And then there are a type of machine learning called the reinforcement learning, which is example of the neural network interacting with the real world processes. For example, the network learning how to play computer game. So returning to my original question is, can we expect the current time of the AI development to continue? And in order to answer this question, we need to look a little bit about the driving forces behind the AI. So during the first and second AI booms, the situation was always the same. So the scientific community comes with the concept and some early implementation. This actually causes the interest in the defense or the industrial community. And this results in the wave of the investment. And then it turned out that the AI was not able to deliver upon this development. So currently, the driving force behind the AI development is actually different. So it's no longer the idea that looks for the application. It is actually the need that is actually mapped through the development of the machine learning tools. So I've shown you this slide in the introductory talk, but before the year 2000, everything has been about the IT. So development of the internet as exemplified in the dot-coms, companies like Amazon and so on and so forth. So by the year 2000, the leading companies in that domain appeared, and companies like Facebook, Google, Uber, and so on has become big. And their primary business model was based on the collecting and searching the data. So Google search is successful because Google can figure out what exactly that you are interested in, and out of the tens of thousands of the possible answers to your search query, Google magically will select the one that you are interested in. So if you experiment with Google search for some concept for yourself and one of your colleagues, you will see that the answers are going to be different because Google tries to give you the output that matches your interests. And of course, as all of you have noticed, there is a very deep level of connection between the way these companies process the data. So the well-known jokes that if you talk about your next to your phone about phishing or something like this, you will start to see the context-oriented ads in your Facebook news lines and so on and so forth. So nonetheless, that was the time before 2010. And then once these companies existed and they have access to all this data, the question has become what can be learned from that data. So ultimately, having the data is not useful. What is useful is being able to derive the insights from this data into the customer behavior and, of course, ultimately monetize these insights. And this is exactly what fueled the development of the deep learning models, because there was a lot of data and there was a need to understand what this data means. And obviously, we don't have physical models for the customer behavior or ad placement or whatever. We need to use the machine learning methods to do that. And the question is, of course, what is going to happen in the next decade? So first of all, it is important to mention that we already start to see the early signatures of the potential, if not the AI winter, but changing the direction of where the machine learning is going. Because the big kids of the blocks now are the foundational models and large language models. By now, they do not require large teams of people to develop them. So in some sense, if machine learning doesn't develop in any new direction, the limiting step would be the operationalization of the large language models, but not the new developments. Furthermore, there is also a little bit of the crisis of the development of the data. So if we have a large language model, we can train it on the Wikipedia only once. We cannot do it second time. And by now, there is already ample evidence that you cannot train the model on the output on the other model. So it does not create the new knowledge. It actually starts to destroy the knowledge in the process. So I have a linked in post where I refer to this as the beige nonsense crisis. So going forward, it looks like that a lot of scientists, including Andrew Ng and many others, perceive that the future of the machine learning is actually integration with the real world processes, both from the point of view of applications and from the point of view of machine learning. And microscopy can be actually an ideal playground for the machine learning, exactly because it's almost ideal toy box for the development of the advanced machine learning models. Now, all this being said, let's go a little bit more in detail about what are the neural networks, how they work, and through few examples of the machine learning application for the real world problems. So just to rehash, the artificial neuron is sort of inspired by the biological neuron. The similarity here is true enough. So in the early days of machine learning, the neuron was suggested by Hebb and Wagner, which are basically biologists. And the idea is very simple. So biological neuron receive the inputs from its dendrites. Once the input jointly exceeds certain threshold, the neuron decides to fire. And basically, it means that it communicates the signal through these axons. And the axons are basically connected to the other neurons. So the machine learning neuron operates almost exactly in the same way. So what you have, simple neuron is essentially a very simple function. It takes some inputs, for example, x1, x2, x3. It multiplies these inputs by certain parameters, so that traditionally called weights. It adds the parameter calls the offset. So it basically just creates a linear combination of the inputs. Then it has been shown that such linear neurons can actually solve some problems. For example, they can solve the linearly separable problems, but in their pure form, they cannot solve the nonlinear problems. And interestingly enough, this sounds like a small observation, but this is the reason why the first AI winter have happened, because at that time it was shown that the linear neurons cannot separate the classification and the XOR problem. So they cannot, there are problems that simply cannot be solved. So it turned out that in order to solve this problem, you need to do two things. One thing is you need to add some form of the activation function. So activation function is generally chosen to be either sigmoid or tangent H or linear rectification, linear unit. But basically what this activation function does, it takes the output of the neuron, this linear combination of the input signals, and then it performs this transform. So depending on whether this input is high, it produces something close to 1, or if it is small, it produces something which is close to 0. That's all there is to it, relatively simple. But such nonlinear neurons by itself is also not very useful. When they become truly useful is when you connect multiple neurons into the neural network. So this is something that you have seen many times, which is the combination of the neural networks and the fully connected network. So in this case, we start with the input layer. So this is just the layer that we inform by the data coming from the outside. This input layer produces this. So this is just the input. So this is nothing changes here. Then we take the inputs and multiply it by the weight vector and add the offset. And we inform all the neurons in the second layer by this linear combination of the weights and offsets. Once we do that, we apply the nonlinear transform. So this nonlinear function shown on the previous slide. And then we create the outputs. And these outputs are going to be passed on to the next layer. And then this process can be repeated several times until we come to the output. And of course, output can be a single neuron if we deal with the with the regression problem or one-dimensional output in general, or it can be multiple neurons at the same time. So the important terminology that you need to know is the input layer. So this is how we communicate and send the input to our network. Hidden layers. So the minimal neural network has to have at least one hidden layer. This would be a shallow network. If we have many hidden layers, that's going to be a deep network. And then, of course, we have the output layer. So generally, the process of the neural network operation is just the information flow from the input to the output. That's how the neural network operates. The question that you can ask is why the system like this will produce anything useful, and where are we going to get these weights in the first place? So just if you estimate, even if our input vector has only 100 components, and we have two hidden layers, let's say 30 and 10 components, then we are going to have more than something like 20,000 of the weights. So that's a lot of parameters that we need to learn somehow. And this is also the reason why the classical scientific community, for example, physics community, have been exceptionally skeptical about the neural networks for a long time. Because in physics, it is well known that if you have a function that you want to feed the data, if this function has a lot of parameters, then you can pretty much fit everything, and the fit results are going to be sort of useless. So one of the famous scientists said that if I have a function with 5 parameters, I can use it to fit the elephant. So in this case, we have functions which has 10,000 parameters, tens of thousands of parameters, even for relatively shallow networks. If you deal with the modern large language models, they have tens of billions of parameters. So where would all these numbers come from? And interestingly enough, that was the reason for the second AI winter. So if we can create the networks like this, but we cannot define the parameters, they are not particularly useful. And this brings us to the most foundational concept that we are going to discuss today, both to the lecture and in the hands-on practice, which is the training of the network. So here, the way the neural networks work is the following. We start with the input, we send it to the first hidden layer, then it goes to the second, whatever hidden layer, and then we create a prediction. In the beginning, our neural network will be initialized by random numbers. So there are different strategies of how to do that. So obviously, if you initialize all the network by zeros, the output would be zero. So there are reasons why it is a very bad idea. There are ways to initialize them better, worse. So the very popular one is the way to initialize the network developed by the Javier Glorat, but practically it can be just numbers, randomly selected numbers from the Gaussian distribution. So if we have the input and we send it to the neural network and perform the set of the neural network operations, then activations, then again, summing, adding numbers and activation, we'll get some prediction. And this prediction will have nothing to do with the reality. It would be just some abstract number. But the interesting thing is that we also have a target. So when we talk about the supervised learning, we always have pairs of the inputs, which are called features, and the desired predictions that are called target. So once we start with the input ascended through the network, the prediction would have nothing to do with the target. It would be whatever random number. And what we do in this case, we define a loss function. So loss function is basically a measure of how the prediction is different from the target. In some sense, it is us telling the neural network how wrong it is. And then what we can do is we can take this loss function and we can backpropagate it through the network. So since this course is actually focused on the applications of the neural networks and not going to look deeply under the hood, I'm not going to go through the details of the backpropagation process, but it is essentially the application of the chain rule. So if you understand what is the difference between the prediction and the target, you can figure out how to adjust each neuron value inside the network in order to get it a little bit better. But suffice it to say that the invention of the backpropagation basically made the neural network what it is now. There are very few architectures that use methods other than the backpropagation. So if we do that, our prediction is going to be a little bit better. And the way the neural networks work is that we are going to repeat this process, give more examples of the features and targets, and do this backpropagation process of the errors over and over again. And this is how you train the neural networks. So this is both a brilliant concept, and it's also the source of virtually all the problems that the neural networks have. Because, for example, for complex networks, you never know whether your predictions will work well only for the chosen examples or whether they will generalize. So this is the cause of the overfitting problems, and a lot of neural network engineering actually deals with solving this problem. That being said, let's look a little bit in detail what type of tasks can machine learning can do. Neural network can do. And this type of task is basically closely related to what are the features, what are the targets, and what is the loss function. So the classical problem that we have in neural networks is so-called the regression problem. So regression means that our target is the continuously varying property. So simplest example of the regression can be is that you present the network with the pictures of cats or dogs or something else, and you want the network to predict the height based or weight based on the image. So I mean, height is trivial. That's actually the case where you shouldn't be using the neural network, but weight may be a little bit more complicated. So this is an example of the regression problem. We want to predict a continuously changing parameter. Of course, it can be more complex than just one parameter. It can be the body mass index, the weight, you choose it. And in this case, the typical loss function would be the root mean square error or the mean absolute error. So just something that determines the difference between the two continuous numerical measure. So the second type of the problems that we can deal with is the classification problem. So classification is very simple, conceptually is that imagine that you have the images of cats and dogs, and you need to separate this, classify the new images, whether they are cats or whether they are dogs. So of course, this is a trivial example. Most of the time, we'll have to deal with the considerably more complex problems. For example, Classical example is something like a MIST dataset, the recognition of the handwritten digits, or it can be a more complex examples like the cipher datasets when you have the ImageNet itself, and so on and so forth. So in this case, the typical loss function is so-called the binary cross entropy, which basically defines whether your classified objects fall in the last right class or not a right class. So generally, once you have the neural network configured, everything else becomes the selection of the right feature set. So first of all, let's start with the definition of the problem. You need to define what is your feature. You need to define what is the target. Secondly, you need to define what task do you want to perform. Is it a regression task or is it a classification task? And then with this in mind, you start to build the neural network to solve this particular problem. Some of this thing in building the network is obvious. For example, the very important operation is the activation function in this last layer. So for example, if our output is a softmax function that can change from 0 to 1, we will not be able to predict anything more than 1. So for regression problems, we need to speculate how large can be our predicted target can actually vary. For classification problems, there are tricks of how you use the softmax or other forms of the predictive probabilities. So that is actually relatively simple, and it can be explained reasonably well. The difficult part is configuring the network by itself. So this is the case where there are a lot of books written about how to do that properly. So I personally recommend the book by François Cholet, the guy who invented the Keras, and Ravel Atienza. So I provide the links to them in the tutorial. There are many other books out there which basically bring you through the whole process of the engineering the neural networks, how to build the intermediate layers, how to introduce things like the dropout layers, what are the problems with the overfitting and underfitting, and so on and so forth. So based on my personal experience and experience of my colleagues, the only way to learn these things is to choose a good book and basically go from beginning to the end, and then do it for the several projects of your own. So there is no way to learn this type of things academically. It's actually engineering in the best meaning of the word. This being said, let's look at several simple examples of what we can use the neural networks in microscopy. And let's start with the simplest examples of the use of the shallow network. So interestingly, by now, we actually don't use a shallow network. So I picked a few examples from about 10, 15 years ago. And one of those can be the identification of the material based on the EELS spectrum. So imagine that you have EELS spectra from several locations. You know that the EELS spectra belong to the several material classes. Can we create a neural network that will recognize the material based on the spectrum? So entirely doable. So the way we typically proceed with this type of problems is, first of all, we start with a data set, and we always start with exploratory data analysis. So in the real world problem, you are never really given the features and target. You have to create them. In fact, another big difference between the sort of academic studies of the neural network and the hands-on studies of the neural networks is that when you take a course, you are typically given an example of the problems where the features and targets are given. Then you are guided in how to build a network that allows you to make the best prediction. It doesn't work like this in the real world at all. In the real world, you deal with the physical problem, or physics problem, and then you need to define it in terms of the features and targets, and then you need to build the best solution for your problem. And what's interesting is that in many cases, the best solution would be neural network based, but not always. So that's something to keep in mind. So following this principle, let's start with a very simple example of the EELS on the heterostructure formed by the calcium titanate and strontium titanate. So we have a hyperspectral data set. We can send this data set to the PCA analysis. So the principle is that we always start with the unsupervised exploratory data analysis. And then if we look at the resulting PCA images and the PCA components, it is very clear what is going on. So first of all, the first two components clearly show that our image is split in two parts. Makes perfect sense. You can conclude that one of these parts is responsible for calcium, another is responsible for strontium. So we see the fourth and fifth component, which are actually uniform, so they don't show any variability. So the obvious guess is that this component is somehow related to titanium, because we expect the titanium layer to be continuous across this interface. And that's what we see here. All the other components are essentially noise. And we know that in this particular case, some of them have grabbed the cosmic ray signal, some of them are basically nothing. So this is as simple as it can possibly get. So the way we create the training set here is we just take few spectrum from here and declare it the label 1. We create the second part of the training set by taking few spectra from here, and we declare them to be the component 2. So we have spectra and targets. And then let's see what happens if we create a shallow neural network with just one layer of the linear neurons. And it turns out that in this case, it worked remarkably well. So once we train this network, it becomes essentially a linear separator, which basically told us that the component 1, which is the calcium titanate, is all sitting on the left, and the strontium titanate is all sitting on the right. We can represent this as the relative fraction just for convenience, so using the color encoding. So the question becomes, how is it different from the principal component analysis? So why would we bother in the first place? The answer is very simple. So principal component analysis, as well as any exploratory data analysis, essentially takes our data set and splits it into the independent parts. That's all it does. When it does so, it is up to us to come with interpretation of the data set. And in this case, I can say, hey, this is calcium, this is strontium, this is titanium, this is also titanium, this is the noise, but this is the interpretation that is based on me reading all these data sets at the same time. That's all there is to that. Once I use the neural network, in this case, I expect to get the answers that have a well-defined physical meaning. And this physical meaning is actually the fraction of the phase. And it actually works. So in this case, my outputs actually have a feeling. Notice the scale bars. Here, the scale bar is whatever the PCA signal components are. Here, the scale bar are essentially the linear fraction of the calcium titanate versus the strontium titanate. And the sum signal tells me how wrong do I think I am. Now, let's see what happens if I create the nonlinear neurons. So in this case, I train my network to predict the classes from 0 to 1. And in this case, this is calcium titanate, this is strontium titanate. So in this case, this is a nonlinear separation, phase 1, phase 2. So what about more complex examples? So in the linear methods, the second lecture, I've shown you example of the linear mixing using the example of the strontium titanate, lanthanum strontium manganate BF4 interface, when we use the supervised mixing to find out the individual components. So in this case, the PCA components are considerably more complicated. So in this case, you can see that the first three components seems to be sensitive to the phases themselves, but the higher order components still show some form of contrast. So some of them are clear instrument related. So this is the instrument not working particularly well. But there are some anomalies appearing in the EELS spectra that PCA actually shows up. Can we make the neural network work for that? We can. The problem is this case becomes that the prediction of the neural network start to depend on the complexity of our input data set. So this is a shallow network. We train it based on the PCA components. And it turns out that if we choose the 3 PCA components or 4 PCA components, is just separate the phases. Once we start to choose the more PCA components, it start to show progressively more anomalies at the interfaces. Is it real or is it not real? The answer is that we don't know. So in the absence of other evidence, we cannot say whether this is the case of the neural network being overfitting or this is something else going on. So what are the cases? How can we use this type of approach? So I don't have a good example coming from the field of electron microscopy, but roughly at that time, we actually played with the same type of approach for the scanning probe microscopy. And the problem that we dealt with is, interestingly, the identification of the bacteria of the surface. So simply based on the shape, we know that this is one type of bacteria, which is called the micrococcus, which is gram-positive and spherical. And this is the second type of bacteria, which is gram-negative and rod-shaped. So we can identify these two bacteria based on their shapes only. But notice that we also have other bacteria here that we cannot identify nearly as well because of the non-ideality of the imaging process. What we can do, however, we can get some spectra on top of this bacteria. So we put our probe and we apply a certain set of the electrical bias and we generate some response. We know that the physical model behind this response is very complex and we actually don't know exactly where does it come from. I mean, we know where it comes from, but we don't know how to quantify it. The question that we have is that whether we can use this response to separate two types of bacteria. The reason why we want to do that is because it is much easier to measure spectrum here and here than to get a high quality image of the whole object. So measuring a local spectrum is an easier task than the visualization. So first thing we try to do is to play with the principal component analysis, and it sort of worked. You can see that different type of objects have different responses, but practically it's not good enough to separate the bacteria based on the response only. So if we take just one component, we can see that there is too much variability here. We actually need to rely on the human eye to recognize the shape of the bacteria inside the image. If we just take the histogram and try to say that everything that has response higher than this one works and everything that has the response worse this one doesn't work, it's not going to work at all. And this is the case where the neural networks actually give us the solution. All we have to do is to take our signal, pre-process it using the principal component analysis, send it to the neural network, and use the neural network in order to predict the class of the bacteria. And this is the example of how it worked. So this is our total image. This is our training region. So we are confident in the answers here. So we trained our network using this part of the image. And then based on this training, we tried to predict the background and the two classes of the bacteria elsewhere. And as you can see that it worked remarkably well. So the first class of bacteria is predicted only for this object. And interestingly, there is something here that we kind of don't quite observe. So it looks like a little bit, so something is going on. So this is the second class of the bacteria. And this one actually works spectacularly well because, first of all, we, of course, recognize the bacteria on which we perform the training. We recognize the other bacteria that we are confident on. For this particular object, we don't know. Maybe this is the same type of bacteria, maybe not. But our recognition imaging shows that this is absolutely not the same type of bacteria. It is something else. some form of the contaminant. And interestingly enough, in this case, it looks like the bacteria kind of got destroyed by our imaging process, but nonetheless, the shape is still identified as the bacteria that we're interested in. So this approach works, and it basically allows us to use the spectroscopy to identify the objects that are difficult to image. So this is what we call the recognition imaging of bacteria, and the principles here and for EELS space identification are, of course, absolutely the same. Then you can ask the next question. So I've shown you the example of the supervised learning when we have the examples, meaning the features and targets from the experiment. But can we solve the different type of problems? Imagine that you have a theoretical model. So it can be something related to the simulation, like Gerd have shown. Can we train our network using the theoretical model and then apply this thus trained network towards the solution of the experimental problem? So this sounds as a very appealing task, a very appealing challenge, sorry, because we typically have access to theory, and theory essentially costs us setting up the program and then calculation. Experiment, of course, costs us doing the experiment. So can we train the neural network using theory and apply it to experiment? So this is something that, again, we explored, started to explore about 10 years ago. And it turns out that the answer is, of course, fairly long and nuanced. It is possible in some cases if the theory matches experiment closely enough. If it is not the case, we need to use the framework of the Bayesian active learning. And I'll show you the examples of how to do that in about a month from now. But for the time being, let's start with the simplest example of training the network using the examples. So the problem that we try to solve is the use of the Ising model in order to simulate the hysteresis loop and then train the neural network using this model and then apply it for the real world data. So just as a reminder for those of you who have not encountered statistical physics, Ising model is basically a model of the spins on this lattice that interact with their neighbors, and the interaction is given by a constant called the exchange integral. That's it. So it's basically the interaction, you consider only the near next interactions. So the way you make this model interesting is you add a little bit of disorder to it, you play with the strength of coupling, it can be positive, and then the model is ferromagnetic. It can be negative, and then the model is anti-ferromagnetic. Point is that the model works. We don't have the numerical formula for that, but we can easily simulate it, and we can get the hysteresis loop that looks very much like the experiment. So great. We can obviously simulate the model responses under many different conditions. For example, if it is in the paraelectric state, we don't have any hysteresis loops. If it is ferroelectric, we can have loops of different shape. If it is antiferroelectric, we can have antiferroelectric loops. So basically, it reproduces qualitatively something that we can see in the experiment. And we made few examples of experimenting of whether this model can recognize itself. And the answer is absolutely yes, beautiful. So if I train the neural network based on the output of the model, and then I apply it for the different round of simulation, the model can recognize the parameters of the simulation. That's actually a big thing, even now, because our measurable in the hysteresis loop. Our unknown are the local parameters of the interaction inside this model. It turns out they can be very reliably determined based on the shape of these hysteresis loops. So as you can see, this is almost the ideal straight line. So the answer is what I expected to be. It turns out that it can even generalize. For example, if I, rather than having the normalizing model, I take an Ising model which is out of the distribution. So rather than having the distribution of parameters, I take a Bernoulli distribution where some of the coupling constants are positive with the probability 1 minus p, and others are negative with the probability p. I can apply this type of fit to the the model, and the answers will end up being very plausible. So I just see that depending on P, our average strength of coupling changes linearly, and our disorder gives a reasonable value. Notice that in this case, I found some effective parameters. So of course, I did not discover the local model, but what we discovered is that the averaging works remarkably well. So now this type of problem is something that you can solve as the second year undergraduate student in the computer science course. 15 years ago, that was actually a pretty big thing. And then the question becomes, can you apply something like this for the analysis of the experimental data? So it took quite a while. And the short answer is that it didn't work remarkably well. In fact, the best fit that we were able to get looks something like this. And then you can ask a question of why. And the answer is out of the distribution shift. In fact, most of the time, when you hear that the neural network trained for some specific problem does not work in a different setting, out of the distribution shift is the explanation. For example, the reason why we don't have the automated cars is out of the distribution shift. If you train the neural network under a certain set of conditions, it will not generalize for a different set of conditions very well. So in some sense, the reason why the neural network trained on theory did not generalize to the experimental data is also the out-of-distribution shift. In other words, the experimental data is generated by a different process than the modeling, and even on a fairly shallow level of description, we cannot match them well enough. That's the reason. In other words, if our theory does not represent the experiment well, then neural network cannot be used to actually connect them. And going forward, the problem that we are going to deal with is how to partially get over that. So the lecture on Friday given by Ayana Ghosh would be an illustration of how we can actually make the neural network work under the different microscope conditions. So this being said, I've shown you a little bit of the past history. So what changed in the last decade? So first of all, the convolutional neural network appeared. So a convolutional neural network solves one of the very big problems, namely the problem of the dimensionality. So if I have an image can have, let's say, decent image would be 512 by 512. So 512 by 512 is essentially 250,000 objects. So if I build a neural network, it will already be a size of the large language model. It is very unlikely that I would be able to train it on any type of laptop that I can buy in the next 10 years, and given some hardware constraints, probably ever. So why is it a problem? It's a problem because, so why is it so? It's so because we are connecting each neuron to each other neuron, so in the dense architecture. How can we solve this problem? So the way this problem solved, as proposed by Yan LeCun, is by treating our objects as a patch by patch. So if it starts to resonate with you with the patch-based analysis of the images that we discussed in the lecture 8, that's exactly the reason why. So you always assume that in the image, in terms of meaning, this part are closely connected in terms of what they mean to each other, and this part will be connected differently. So the convolutional neural networks actually use this, and in the next lectures, Ayana and Tommy are going to discuss how they're built and how do they work. But generally, the way we use deep convolutional networks is by starting with image data, going through the set of the convolutional transforms. So this is very often called the convolutional funnel. And then after a while, we start to switch from the convolutional architecture into the classical fully connected so-called multilayer perceptron or MLP architectures. So what can we use the convolutional networks for? So as I mentioned, the typical example is the semantic segmentation. So this is a cat This is semantically segmented cat. So the network identified what part of the image is occupied by the cat. Another example is the classification. So classification would be to say this is a dog, this is a cat. The difference is that you just identify, but you don't say where it is. And of course, we can use it for imaging data. So for example, you can take an image from the microscope and you can semantically segment it into the domain walls, and we will discuss how to do that. So before we go with the collab, let me illustrate a few examples when the deep learning actually worked for the real world examples in microscopy. So the movie on the left is the set of STEM images of the material evolving under the action of the electron beam. So this is a tungsten sulfide. You can see that when the electron beam irradiates it, it creates the point defects merge, and then the whole material starts to fall apart. So an example of using the deep learning to learn something from this data is to train the network that is going to find the defects, point defects, but nothing else. So this is a defect sniffer type of network. So notice what happens. The network ignores the large objects like holes or the clusters of the second phase, but it actually follows the individual point defects, and it actually classifies the point defects as they form. And with this type of neural network, what we can do is we can take a movie of 100 frames and convert it into the space-time trajectories of the individual defects. So this looks a little bit psychedelic, so it's kind of difficult to understand what this image means. But basically, this is a trajectory of the different type of defects. So you can see that some of the defects stay in place. So they look like fixed locations in X, Y. Some of the defects seems to be moving around a lot, like this one. So they seems to be in one place and then they sometimes shift around. And some defects just appear and disappear. So appear and disappear, this is just a recombination generation processes. The ones that move around, we can estimate the diffusion coefficient. And actually it turns out that it's even more interesting than that, because for the defects that stay in place, we can actually analyze them, and we see that this is not the same defect. In fact, it looks like that there is something that stays in place, but the defect itself changes kind of shape. So this is the case where we went forward and backward between ourselves and theories several times, and we were able to solve this problem and find out that this is most likely the molybdenum on the tungsten side. It can be the pure molybdenum on the tungsten side, or it can form a defect pair with a sulfur vacancy. And sulfur vacancy can be in the 3 possible orientation with respect to the molybdenum. So this is our 4 defect classes, and we actually learned it from the analysis of the data. We didn't know that they exist. We observed them, we extract them using the deep learning, and then we were able to identify them from the physics viewpoint. And then the really cool thing was that if you observe the process like this, you can actually reconstruct the Markov transition matrix, which is essentially the reaction constants in the system. So this is a more complex example of the machine learning, where we solve the full segmentation problem rather than defect identification. So this is a graphene image. So this is a hole. This is the graphene. The bright dots are the silicon atoms. And this is the example of the semantic segmentation, where we identify this image as either carbon or silica. So this is something that we've done almost 8 years ago by now. And for 6 years out of the 8, we were working on how to make this type of analysis work in real time. And this is something that Ayana is going to talk about on Friday. So once it works, what else can you do? So it turns out that sky is the limit, right? So the type of problems in physics you solve with this type of capability is entirely up to you. So the type of thing that we thought about, but that's obviously the very beginning, is taking the microscope image like this and identify all the possible configurations of the atoms inside this image. So this is building the libraries of the defect. So if we take several hundred of the images of the material under the microscope, identify all the atoms, we can start build the libraries of the defects that clusters that are formed inside the material. And once we have these clusters, we can actually connect them to the electronic structure calculations and determine their individual electronic signatures. And in a few cases, we're even able to visualize them directly under the scanning tunneling microscope. Of course, minus the operation of the sample transfer through the through vacuum. It's possible to identify the structural elements in more complex situations. So once you have the segmentic data, it works. And for example, we can identify the edge configurations of the silicon atoms in the graphene. The problem here is that we need to somehow deal with the rotational variance, and this is what we are going to discuss in the lecture of the rotation invariant autoencoders. And of course, the same approaches can work for more complex situations. So identification of the atoms in electron microscope is a relatively simple problem compared to the scanning probe microscopy, because atom is ultimately a delta function. And what you see on the screen is the convolution with this delta function with the nucleus. It turns out that we can use the deep learning for much more complex problems from the imaging point of view in a scanning probe microscopy. For example, identify the particles in the images like that. So this being said, just to finalize the introduction lecture part, the development of the machine learning methods over the last decade followed approximately the following pathway. So something like 2010, we dealt with the, of course, we had the electron microscope, including aberration corrected ones. We had the big data problems. The problem at that time was the availability of the neural network. So then we only had the shallow ones. Somewhere around 2015, the problem have been the computation. So the deep learning network exists. Keras and related frameworks were already available. The problem was the availability of the computational resources. So I personally didn't have an access to the GPU at that time, and I didn't know how to use it. Currently, we are in the place where the deep neural networks are well developed, relatively easy to use. The primary challenge is connecting them to the instruments. But thanks to the Neon Swift or PyGem or equivalent interfaces from the Thermo Fisher and so on, by now it's actually becoming doable. So the limiting factor is actually a human barrier, meaning learning how to do that. And with that, let me switch to the Mani as the, okay, where are you? Here you are.
I'm here, yeah.
Excellent. Mani is the co-host, and he is going to guide all of us through the notebook, which allows us to actually play with the neural networks. So then, as a reminder, the notebook is on the GitHub. So please open it in the Colab and take it off, Mani.
Yeah, okay. Let me just give you the link to the notebook in the chat so that you guys don't have to go through all the process. So can you guys hear me and see my screen at this point?
Yep.
Okay. Okay, I'm Mani Valeti. I'm a graduate student working with Sergey for the past 4 years. So I specialize in applying various state-of-the-art machine learning techniques to microscopic data and try to understand the physics that is communicated by different materials through the data. So that's about me. So before I start the tutorial, I had a couple of general comments to the public. So if you have already coded a neural network in Python, so you can use this tutorial as to brush through the basics of neural networks. But if you haven't, I implore you guys to make use of this tutorial to understand the vocabulary and the building blocks of the neural networks, because I think we are going to pick our pace from the next lecture or so. And without knowing what these building blocks are or without understanding what each of the vocabulary that comes along with the neural network means, it is going to become extremely difficult to follow the upcoming lectures. So with that said, for this tutorial, we're going to need a GPU. So the way you access GPU on Colab is if you click on runtime on the top here, and if you click on change runtime type, it lets you to pick different hardware accelerators, which are GPU and TPU. For now, I'm picking T4, which is like the least expensive GPU provided by Colab. So I have the Colab service subscribed for $10 a month. If any of you guys do not have this, and if the Colab doesn't allow you to pick a GPU, you can still run the notebook, but it's going to take minutes where it's supposed to take seconds or so. But you don't have to do this because the collab is already initiated to pick all of these beforehand. So the collab is already initiated to pick GPU and a T4 GPU. So that said, I want to start the tutorial by introducing you to one of our favorite datasets called MNIST dataset. So MNIST dataset is a bunch of handwritten digits presented in a grayscale image of size 28 by 28 pixels. So we are going to download that dataset from Keras. So I want to clarify a bunch of things. So since some of you guys aren't used to the vocabulary that is being used here, what's TensorFlow and what's Keras that is being used in this notebook. So TensorFlow is a high-level Python package written by researchers at Google to implement deep learning in Python, whereas Keras sits on top of TensorFlow, which is an API, which makes the code more convenient and less and easier to understand. The code itself has fewer number of lines when it is compared to TensorFlow. I can start by giving an example or a specific analogy where if you are trying to if you imagine building a neural network as a task of building something with Legos, TensorFlow gives you the most basic blocks of Legos, and with those Legos, the number of combinations that you can form are virtually like infinite. So, but what Keras does is that if you're trying to build a house, it gives you like pre-built walls, windows, doors, and stuff, so that you can put all of them together. So you have this convenience, which and you also save some time while writing the code, but you lose some of the flexibility. So that is majorly oversimplifying things, but so that would be an introduction to what TensorFlow and Keras are. And Keras sits inside the TensorFlow as of now, so you can use Keras to write codes in TensorFlow as well. So coming back to the MNIST dataset, so some of these datasets, standardized datasets, are already present in these packages like TensorFlow, Keras, or even PyTorch, and you can just directly download them using just this one line. So it is loading this MNIST dataset in this line. So these datasets are standard datasets, and again, giving an analogy, if you want to think about them, so these standardized datasets are like the guinea pigs of deep learning. So if you ever construct a new network, and if you want to evaluate the network, how it is working, you might as well try these preloaded datasets in the packages. So that's what we are doing here. So each dataset is itself divided into training and testing images. So if you print out the shape of the training images, so you have 60,000 of them. Each image has 28 by 28 pixels, a grayscale image where intensity of each pixel falls into the range of 0 to 255, which the whole range covers the entire variations of gray. And you also get the train labels, which are essentially numbers. So each number represents the digit that is actually written in the image. We'll see what this mean. So we also have a proportion of the dataset that's put aside, which is the test dataset. It has like 10,000 images, and we won't be using them during the training phase. We'll be using this to evaluate or validate the network that is already trained. We'll see why this is important when we go through the notebook down here. So I want to show you a bunch of MNIST images. So this is what the images are going to look like. So I picked like 9 randomly sampled images. So you can see the digits that are written here, and the corresponding labels that come along with the images denote the digit that is actually written in the image. So the label for this, or the what did we call it? We did call it label. So the label for this is going to be 434 and so on. So here's where we are. So the task here that we are trying to perform is going to be a classification task. So it's important to understand what the input to the neural network is and what the output is and what is the loss function that we are using to measure the difference between the predicted and the target values, and also the optimizer that is being used in the neural network. So these are the four major components. So we'll start with the input, which is this image to the neural network. The output is the label that we are trying to predict, which is 4, actually the digit 4. And the loss function and the other stuff we are going to get more into detail as we go through the notebook. So so if you can take my word for now, so this is how we construct a neural network model in Keras. That's it. It's as simple as that. So it has two layers. One is a hidden layer with 512 neurons, and there is an output layer with 10 neurons. We'll see why this 10 is present here. But 512 is essentially a hyperparameter. The number of layers and number of neurons in each layer is a hyperparameter that you need to know. I mean, you need to know before you construct the network, but you will develop more intuition of how to fix these numbers as we go through the notebook again. And once the model is defined, we are compiling the model here in this line. So this takes care of what type of optimizer we are using, what sort of loss function we are using, and what are the sorts of metrics that you want to consider to evaluate the neural network. We will go into details about every one of these as we proceed along. So So before we actually train the network, it's essential for us to normalize the input data set. So why this is being done comes back to dates back to the origin of the activation functions. So if you can see, sorry, I cannot access my tabs. There you go. So if you can see the activation functions over here, so what we are trying to do is that we are trying to find the gradient of each parameter with respect to the error, and we are trying to tune the parameter so that the error decreases. So we find the gradient of the parameter with respect to the error, and that gradient, if you have very high values, the gradient is going to be 0. Or if you have very low values, the gradient is also going to be 0. So essentially want to operate in this region. So the W times X, that what we are getting here, should be essentially in this region. So our packages make sure that the W's and B's are initialized somewhere very close to zeros. And the onus is upon us to make sure that the X is also normalized so that we essentially fall in this region. So that's what we are doing here. Since the range of the grayscale image was between 0 to 255, we just divide the whole image by 255. Now each pixel's intensity is in the range of 0 to 1. So once we do that, we train the neural network, and again, it's one line code in Keras. You are asking it to fit between we are essentially asking it to fit between the input and the output. So these are the training inputs or the images, or these are the outputs, which are the labels. And we are asking it to do it for 5 times, and each batch has 128 images. So we do not, so because of memory constraints, we do not take the entire data set and use it to update the weights and biases. We do it in batches. We take 128 images at a time. We calculate the gradients, we tune the parameters, and then we go back to the next batch. And once we do it with all the batches, like 60,000 by 128, how many ever batches it is, it's actually 469 batches. So that's called an iteration or an epoch. So once that's done, we are asking the neural network to train for 5 epochs. So it does go through all of those batches at each epoch. So at the end of the 5 epochs, we have the loss as 0.036, which does not have any meaningful value over here, which is why we gave a metric called accuracy, where once the training phase or once the training phase is complete, the network evaluates the accuracy of the predictions on the data set that we have. So 90.9889 essentially says that out of 100 images, every 98.89 images are correctly classified by the neural network. So this makes more sense, and this is where metrics come into play. So these metrics are not used while training the network, but these metrics are used to evaluate the network once it's trained. So we can give it a bunch of these metrics, and it's going to print all of these metrics at each epoch. And you can see how the training is being carried on by reading these accuracies. And the loss function is essentially has to decrease, but there's no physical meaning associated with the loss function that a user can read. The loss function is for the neural network or for the keras to optimize the neural network, and the accuracy is for us. So that being said, so here's the predictions of the neural network, and here we'll go into the activation function that is used in the last layer, which is the softmax activation function. Just for an example, so I take one of the digits of a random digit, and I'm trying to plot the prediction of that random digit, and I'm also plotting the image that corresponds to that particular data point. So the particular data point being 9, and this is the output of the neural network. So how to read this is the predicted probability of each class as predicted by the neural network. It's extremely confident that the image is 9, but it is also ascribing some probability to image being 3 or 8. So, so this is what happens, but this is essentially being done by the softmax function. So you have 10 neurons in the output layer of this particular neural network, and each neuron predicts a value which is proportional to the probability that the image is associated with that class. So what softmax does is that it takes those values. Those values essentially do not have any meaning on their own. So it takes those values and it projects them into this probability space where you can read off probabilities by just looking at this plot. It does not do it in a linear fashion where you can imagine dividing each value by the sum of all those values, but it does include an exponential function, and there is this projection that's been happening from those 10 values through this softmax function for us to get this probability distribution or this histogram. So what the target function is going to look like for this image is going to be 1 at 9 and zeros everywhere. So that's the ideal target that we are trying to predict. That's the label of the image that we are trying to give it, that we are trying to predict. So it's going to be 1 here and zeros everywhere. What the loss function is going to do is it's going to measure the distance between this probability distribution, the probability distribution that you're seeing, the predicted probability distribution, and the actual probability distribution, which is 1 here and zeros everywhere. So it's a probability distance, not a linear distance. Again, it has some logarithms involved in it, but if you want to go check it out, you can search for it on the web. So once that's done, we just see what the accuracy and how the network has performed, and we on the test dataset, now we are validating the dataset that is already trained, and we got an accuracy of about 98% on the test dataset, which is actually good. So we'll get a feeling for all of these numbers, what 97% accuracy means, what is this loss function mean, and what the rest of all of the things. So the point of this tutorial is to develop an intuition, and I'll try my best to communicate and help you develop an intuition for all of these particular entities. But yeah, so that takes us to the next section where we build a neural network from scratch. This is where we understand what each component of the neural network represents, how it is trained, and all of the other things. So to train a neural network, first we need a sample data or a synthetic data or a very small data set that we are creating by ourselves. So the data set is being sampled by two different Gaussians. We'll call this normal distribution or a Gaussian distribution, a negative normal distribution, and this is the positive normal distribution. So these two have the same covariance matrix, but have different means. So it's a two-dimensional Gaussian distribution. If you call those two dimensions x1 and x2, which is what we'll use for the rest of the lecture. So the x1 is 0 here and x2 is 3 here. This is the mean of the negative Gaussian, and this is the mean of the positive Gaussian, where x1 is 3 and x2 is 0. So once we sample like 1,000 different data points from this class and 1,000 different data points from this class, we just stack them together. And we also get the targets. We also handwrite the targets, like hard code the targets. That zero is the target for the negative Gaussian, and 1 is the target for the positive Gaussian. So this is what the dataset is going to look like. Each data point is colored by the target label, which is 0, 0. Purple denotes 0 here, and yellow denotes 1 here. So the next cell is going to define a neural network. It's going to train a neural network, and it's it also going to plot different plots during the training process. So this is how we are going to do it. So our neural network is going to be of the form y equals w1 x1 plus w2 x2 plus b. So the x1 and x2 are the features. These are the features of the data set. Each point has a distinct value of x1 and x2. And b, w1, w2 are the parameters that we are trying to optimize. And y is the target that we are trying to predict. It should be 0 for all the purple dots and 1 for all the yellow dots. It cannot be, we cannot do that just by using two parameters, but we'll ask the neural network to learn what it can. This way, I can't even call this a neural network. It has essentially one neuron, but we'll ask it to learn what it can, so that we'll be able to understand what it's actually doing. So we first we initialize the parameters w and b. As I said earlier, they should be very close to 0. W's are initialized so that are randomly sampled from a uniform distribution with a minimum value of 0 and maximum value of 1, and b's are set to 0. They'll even the b is set to 0. There's only one b here. They'll eventually get tuned so that the loss function is meaningless. So the loss function here is the squared loss or mean squared loss between the targets and the prediction. You take the difference, you square them, and you then reduce it using mean. So, and we also have a learning rate. We'll discuss the learning rate when we discuss the optimizer that's right below here. So the learning rate is set to be 0.1 for now. So what we are actually doing is that it will help me if we have this. Yeah. So what we have to do while training a neural network is that we have a bunch of inputs. We do a forward pass, whereby I mean that we get to the predictions of the neural network. Then we compare it with the target using the loss function. We essentially get the difference between the target and the prediction using the loss function. Then we get the gradients of the loss function with respect to these parameters. So what we are actually doing is the gradient descent in the parameter space, whereby the our function is the loss function. So we get the gradients and we use the gradients to tune W's and P's or all other parameters that are present in the system. So this is what we are doing here. So TF dot gradient tape is where, so TensorFlow actually, whenever you define a network, right? So it creates a graph where each node is a mathematical operation. So it keeps track of all the forward propagation as a graph. So when you use this statement, it also computes the gradients of each parameter and stores it there, so that we can use those gradients later whenever we want to actually train the neural network. So that's what this gradient tape is doing here. And the forward pass happens like this: predictions equals model of inputs. So that's it. That takes care of the whole forward pass. Now we are evaluating the loss, which is the square loss between targets and the predictions. Predictions we get from here, and targets we have already hard coded them. So now we get the gradient of error with respect to W and gradient of error with respect to B. So essentially, if you have a large neural network, you have to do this for every parameter, which is why we need a GPU which parallelizes everything, and everything is done on multiple core on different cores. So once you get the gradients, you update the W and B using gradient loss times learning rate. So what this is actually doing is W equals W underscore old minus gradient times learning rate. So this is what the learning step or the tuning of the parameters is going to look like. Once that's done, so we get to the next data point. We get to the next data point. That's how we do it. So we do it for 40 iterations. And here we are not using in batches. We are using the whole data set at a time because it's only 2,000 data points. And at each step, we are trying to plot a line where our function actually predicts 0.5. So this is which is like the decision boundary. If it predicts more than 0.5, it's going to be 1. If it predicts less than 0.5, it's going to be 0. So this is what the training boundary is, or the boundary during the training process is going to look like. I guess it started somewhere over here. You can animate it if you can take this code and animate it and see how the boundary changes. So it might have started somewhere over here, and as we tuned W's and B's, it went and uh, it went and stayed somewhere over here. So that said, these are the final outputs and right what? Okay, so these are the final outputs of the neural network, and this is the final decision boundary that the neural network has learned after 40 iterations. And we are using the predictions. So if you look at the prediction, the color used to color used on the scatter point. So this is what it's going to be. Predictions, if it's greater than 0.5, it's going to be yellow, which is going to be true or 1. And if it's less than 0.5, it's going to be blue, which is 0 or false. That's what this statement is saying here. Uh, so again, we see the loss function, which is the squared loss, and we see all of these values. We have no idea what these values is, what these values are, and there's no way of quantifying the loss function from the user side. And the neural network actually uses its loss function to tune the parameters, but the user cannot make any sense of these the values of the loss function. So in this binary classification problem, we usually come up with something called a decision matrix, and this cell here is used to plot that confusion matrix, which is also called as confusion matrix. So this is what the confusion matrix is going to look like. So the size of the confusion matrix is proportional to the number of classes in the data set. So we have 2 classes. So these are the x-axis is representing the predicted values of the neural network, and the y-axis is representing the targets of the actual values of that are given to the neural network. So the ones on this diagonal are the correctly classified data points. So it did classify 999 plus 997 data points correctly, and there are some data points where the data points were actually positive, but it classified them to be negative, and the other way as well. So there are like 4 of them which got misclassified. So there's this ROC curve, which is also used to do a similar thing of evaluating the network after it's trained. But we'll get back to this if we have time. I want to go through the rest of the new topics about the neural network. So, so this is where we built a single neuron using the TensorFlow, and this is what it took us. So how are carers going to make our daily lives easy is by doing this. So if you want to create a neural network that has an unknown input, you don't know the input at this point, has a hidden layer with 64 units, and has an output layer which is 10 units. And we are again pointing this back to the MNIST dataset. We'll use a Keras network, a network made by Keras on MNIST dataset. So the output layer always has 10 neurons. So this is it. So the model, this is the entire construction of the network. It says the sequential is a keyword which says that you have layers that are arranged sequentially. So the first layer has 64 units, and the second layer has 10 units, and this works. This works like a charm. So the whole construction of the model is done. So how you do your forward pass here is going to be model of inputs, which we have already done, and that's all there is to the forward pass. So there's different ways of setting up these layers in Keras, and each cell is going to go through each one of them, or different ways of going through the what happened here. What happened here? There's something happened here. Okay. Well, you just if you don't want to initialize them all together, you can just start initialize a sequential method from Keras that is already inbuilt, and you can keep adding layers with this dot add method. So when you say model dot add, it expects a layer which is layers dot dense of 64 units, and you are also specifying the activation function to be ReLU, and the final layer activation function is to be softmax, and we have added those layers over here. And when you actually build the model, you can give it the input set. So this is an extremely important feature that Keras has. And I usually work with PyTorch, and which is where we have problems with the PyTorch network. So Keras doesn't actually initialize the parameters until it has to. So once you do this, right? So this is also a legit model. So it doesn't know what the input shape is. even then this still works. When you try and operate this model on some of the inputs, it figures out that the input has like 3 dimensions, or in case of the MNIST dataset, it has 28 by 28 dimensions, and then it initializes all the weights. So you can do this, or even without this, you can still make it work using these statements. So I will come across a case where this becomes really important in as we go through the tutorial, but that's something to keep in mind. And this is how, so if you want to see the actual weights, this is how you are going to be accessing them. Model.weights is going to give you all the weights as a tuple. So it has like four elements, which so since we have 2 layers, so each of the element is going to correspond to the weights or bias of one of the layers. So this is how it's going to be arranged. So weights of the first layer, then biases of the first layer, then weights of the second layer, then bias of the second layer. So we only have 2 layers, we only have 4 elements, and you can also see the shape of the weights. So since we already gave it the input to be the size 3, the weight matrix is going to have the shape of size 3, 64. By the way, if you ever want to know what the shape of the weight matrix is going to be, it's the input, it's the dimensions of the input layer times the dimensions of the output layer. So which is 3, 64, and the next layer is going to have 64 times 10. So because there are 10 neurons in that layer. So that's what we see here. So 3, 64, weights of the first layer, bias of the first layer, which is 64, weights of the second layer, 64 times 10, then bias of the second layer, which are only 10. And you can also print this model summary to tell you what the model has been. This is just to visualize how the model is constructed, and it's going to give you a nice looking table where it enumerates all the layers that are present in the network with the number of parameters that are already present in the network. So this neural network has 906 parameters, and all of them are trainable. So there are some rare cases where you do not want some of those parameters to be trainable, and Keras does that as well. So if you fix any of these parameters, this will not get updated when you're doing the when you're like back propagating the error. So this is used uh, when you're doing transfer learning, which is not the scope of today's tutorial. But yeah, so another way of defining layers in the Keras is that you can give names to the each layer, and you can also name your model as well. So that's what we are doing here. So model is named as my example model. Then we add a layer with my first layer, and then we also add a layer called my second layer. 64 and 10 value on softmax are the activation functions, and we are again providing the input shape, which is going to be none, 3. If I don't know if you guys have figured it out, but none here represents the batch size, since we do not know the batch size beforehand. So whenever the network whenever we perform a forward pass through the network, so this is how the network is going to see the inputs. So it's going to have the shape of the number of elements in each batch times the dimensionality of the data. So if you had seen if you remember the MNIST data set, so we were giving it like 100 data points in each batch, and 28 times 28 is the dimensions of the each image. So that's what the input shape is going to be. But if you do not know the batch size beforehand, we can just put it as none. And we can again call model.summary, and you can see the summary of the data of the network that we just created. There's one more way of creating the data set. There's actually a couple of more ways. So, so we initialize the model as a sequential. We keep adding the layers. The first layer is going to be the input layer with this shape, and then we add the second layer, layer dot dense of 64 activation value. And if you just since we have already given the input layer, we don't need to do the model dot build. And if you call model dot summary, it's going to tell you the layer that it has already added. So once that is done, and if somehow you want to add another layer after training and the network hasn't performed well and you wanted to add another layer, you can just do this model.add, and you can add the statement at a later time, and it's going to take care of everything. You don't have to start everything from scratch. And if you print model.summary, you can see both of these layers added together for the neural network. And the last way of doing this is this is slightly low level way of doing it. So you start with this does not include the sequential argument or the sequential package that we were using. We just initialize the inputs as keras.input of shape 3 and which has a name of my input. So we can use this to create the next layer. So features is going to be layers.dense of 64 units activation value, but we are saying to the network that it's going to act on inputs. So the next output layer, we are going to define the layer, and we say that it's going to act on the features. Now, when we try to create a model, model equals keras.model, input equals input, and outputs equal to outputs that the outputs that we just created, it's going to figure it out by itself. So it starts from input and it forms this map that inputs become features and features become outputs eventually. That will that we can see that if you look at model.summary, and you can see both of these layers here. Okay, now that this can be confusing at times, but you don't have to learn all of this. You just have to know one of these things to set up the forward model. You can pick any one of these, but you can pick one of these, one of your choice, and then you can use that to create the forward model. So that being said, we'll start running the code on the MNIST dataset. So we again load the data xtrain, ytrain, xtest, ytest, MNIST.load data, and we have the train labels and we have the test labels. We just sample 25 random. We just pick 25 random samples from the dataset and we plot all of them just for visualization purposes. And now we start to create the actual neural network. So, sorry, there you go. Okay, so this two categorical function here. So there's two ways of providing the targets to the neural network when you're doing a classification task. Earlier we have seen that we were just giving the labels as 0, 1, 2, 3, or 7, 8, 9, or something of the sort. And these two categorical variables or function is going to create those labels into this one hot encoded vectors that I have showed you before, that probability vector that we have dealt with. So this is going to turn a number 9 into a probability distribution where it peaks at 9 or the 10th index actually, if you're talking about Python, but it actually peaks at number 9 and it zeros rest of the way. So you can do this, or you can also give the targets as 0, 1, 2, 3, or so on. The only difference is going to be specifying the loss function, which we'll see later. You can pick one or the other, it's not going to change much, but the reason why this is usually avoided is that if you have large batches of data, this is going to eat up the memory. So to get rid of that, we don't usually give one hot encoded vectors. You can just give them 0, 1, 2, 3, and it still does the same thing for each batch, but it doesn't do it for the whole data set at the same time. So once we have that, and here's the normalization thing that I talked about earlier, and we are also reshaping the dataset to have the size of the dataset to be one-dimensional. We haven't yet gotten to the convolution dataset, convolution neural network, which can act upon the images. We are still in the deep neural network regime where it expects a column vector which has the size of 784. Look at that. Colab tells me that it has the size of 784. So 28 times 28 is 784. We actually flattened the whole image to be a single vector. So now here we are trying to proceed with the neural network construction using keras. So these are all the hyperparameters that are used in the neural network. So batch size is 128. So it does 128 images at a time, and it goes through all the batches at each iteration. And hidden units are 256, and we'll see what that number represents once we actually start building the network. So we initialize it with an empty sequential keras model object, and then we keep adding the layers. So first layer is going to have 256 neurons, and then you have an activation of ReLU. You can keep adding this one at a time. You don't have to add the ReLU activation function somewhere over here for if you want to do it that way. And then there's something called dropout. We can ignore it this for now because I don't want to confuse you guys. But we'll see if we can get to that at the end of the tutorial. And then you add another layer, which also has 256 units, which is the hidden unit. And then you have the activation function dropout. And then you have the final output layer, whose size is equal to the number of labels, which is 10. So our network here is going to look like this. So there's input of size 28 times 28, which is 700 something. Then you have a hidden layer of size 256. Then you have another hidden layer of size 256. Then you have the output layer of size 10. So that's what we built over here. For the last layer, we are going to add the activation as the softmax. And if we print out the model, that's what it's going to show here, 256. Ignore the dropout for now. So this is the layer 256. There's another layer of 10. Yeah. So if you see the number of parameters that are involved in constructing just this network, so it's going to be 270,322 parameters, which are insanely large by any stretch of the imagination. But that's what you need to get used to these numbers. These are the usual number of parameters that are present in any like so-called deep neural network that you are going to come across. So now we are going to compile the model, which is going to be the loss is going to be categorical cross entropy, and optimizer is going to be Adam, matrix is going to be accuracy. So categorical cross entropy is used when you have these one hot encoded vectors, when you are giving the targets as the probability distribution, where it peaks at one value and zeros at every other value. If not, it's going to be sparse categorical cross entropy, which you might have seen where we discussed the MNIST dataset above as well. See, optimizers. What I have shown earlier when I was playing around with the synthetic dataset, where I was tuning the parameters, is the simplest optimizer that you can ever see. Essentially, every optimizer does the same gradient descent, but it has extra features to efficiently navigate through that error space. For example, Adam optimizer has this momentum factor where if you can imagine a scenario where there are 10 batches, and let's say the 10th batch has a bunch of outliers in them. So those are not the data that the data set is not true. It got spoiled somewhere along the way. That's what outliers are. So once you have this bunch of outliers, the first 9 batches are going to do the gradient descent in one direction. Let's say it's going forward like this, and the 10th batch, which is not exactly is the representative of the whole data set, is going to ask you to move in some other direction. So what does the neural network or the gradient descent should do now? Should it keep following this direction, or should it follow this direction, ignoring all the rest of the other batches? So this is where the momentum factor comes into picture. So Adam has this momentum factor where it goes, where it takes you, where it has the momentum attached to it from the previous updates as well. So since it was moving in this direction for the past 10 steps or so, it's going to move somewhat more in this direction rather than going just in this direction. So it's going to be a combination of these two, depending on how much weight we have given to the momentum factor. So the one other optimizer that we will see as we go along the lecture is RMS prop. So this comes to the value of the learning rate. So we get the gradients, we multiply it by the learning rate, and that's the value we use to update the parameters in the neural network. So if you have a very high value of learning rate, so if you have a global minimum, it's going to shoot past it. So if you were here and the direction that you are going here, it's going to shoot past it. But if you have a very small learning rate, it's going to take a lot of time to get here. And if you have a very high learning rate, you keep doing this. So essentially what RMS prop is going to do is that it's going to have a very high value when you start the learning process, and as you get closer to the minimum of the error, it's going to decrease the learning. So all of these things are essentially performing gradient descent in a very fancy manner. So the downside that we get with all of these fancy optimizers is that they come with a bunch of hyperparameters that are to be tuned for the network to learn properly. And again, so there's no real way to tune these hyperparameters. If you have a very large network, you can all do it through intuition. If you know what a higher learning rate is going to look like, which we'll see, and if you know what the lower learning rate is going to look like, which we'll again see. So that's how you know where you are in that hyperparameter space. And these are the hyperparameters are not learned when we are training the network. These are some of the user inputs that the network expects. So we train the network, and if you see, you can run this cell. It's going to take a couple of minutes if you are running it on GPU. So if you see, it prints out the loss at each iteration. It prints out the accuracy. It prints out the validation loss, because actually when you're trying to fit the model, I not only did I give it the training dataset, I also gave it the validation dataset, which is the X test and Y test that I was talking about, and we also asked it to do 20 epochs. So giving just this, it knows what to do. So it does a forward pass using this X train and Y train. It evaluates the loss function. It back propagates the error. After each batch, it also uses this X test and Y test to validate the network performance. So what the accuracy I'm getting, what's the loss function value that I'm getting on this validation data set. Everything is done by Keras using just this one line. So that's when you run this line, this is what the output is going to look like. After every iteration, it's going to give you the loss, validation loss, accuracy, and validation accuracy as well. And if you plot out the validation losses and model and the both the training and validation losses and training and validation accuracies, this is what is going to look like. With epochs, the accuracy goes up and the loss comes down. And if you see something odd happening with the test loss, if it starts decreasing and then it starts increasing, that's where we call it overfitting, and we can discuss about it further in the lecture. So again, I computed another confusion matrix for this dataset as well. So it's going to have 10 columns and 10 rows, and this diagonal is going to show me the elements that are correctly classified, and the rest of the elements you can read it off where actual two is classified as 0, or some of the other cases as well. So this is how you know how the training process has actually happened. So now that we have seen a deep neural network, now we'll see a deep convolutional neural network, where instead of flattening the images, we'll use the whole image as the input to the data set in its form, 28 times 28. So we load the data, we get the labels, we get the categorical labels, which is again one hot encoded vectors, and Y test is, we also get the labels of the test data. We know the image size as one. We add this dummy channels. You don't have to worry about that. But essentially, each filter in a convolutional layer is going to create a channel. Channel is nothing but just an image. You have multiple in different information in each of these channels. So the input that we are telling to the network that the input data set has only one channel, and yeah. So the input shape is image size times one channel, batch size is 128. Kernel filter or convolutional filter or any of these names all point to the same thing. And pool size is the kernel used in the pooling layer, and number of filters that are used in the hidden layer, and the dropout layer, which you can ignore for now. So to explain what these parameters mean, I need to show you the. So this is what the convolution is, right? So you have a filter, you place it at each pixel, and then you get the value for the new image that you are creating. So each of these filters is going to give you a new image. If I have like 100 of these filters, I'm going to get an image with 100 channels. So each image has different information that it has learned. So that's what the kernel size is going to be. So if you add convolution filters here, kernel size, activation value, input shape equals input shape. So you have 64 filters in this layer. then you also have 64 filters in the next layer. So if there are two convolution layers, at the end of each layer, the image is going to have 64 filters. And then after at the end of convolutions, you also have a max pooling in between them, whereby you are doing this. So we are decreasing the size of the image when you're doing this. And then you flatten the whole output, and then you use a dense layer, which is going to be the output layer, and it's going to have 10 neurons in the output layer. And we use the softmax activation function, and the rest of all is going to be the same as the network that we have already seen. Categorical cross entropy, Adam optimizer that I have already explained, and metrics is accuracy, which we'll use to print out the model, the state of the model. And you fit the model using, again, just this line, and then you also evaluate the accuracy of the model. Once it's done, if you want to use different metrics to evaluate the model, you can use this line to do that. So if you see that with just 10 epochs, you got to a 99.41% accurate. So the test accuracy is about 99.3%, which is much better. The one thing that you have to notice here is that the convolutional network has only 80,000 parameters as opposed to 260,000 parameters by deep neural network. So here's the case. So to play around with the notebook, we created two different cases. So this is the image that we have. So we add additional channel to the image where we have noise in one case and zeros in one case. So this additional channel is going to have, in the first case, as Gaussian noise, and in second case, it's going to have all zeros. And we are going to train two different networks, and we are going to compare the performance of two different networks. And this is the training part. We train two different networks for each of those data sets, and we'll plot the validation accuracy. And this is the accuracy for the data set with noise, and this is the accuracy for the data set with all zeros. So if you have seen any deep learning lectures, people keep telling you that neural networks are extremely good at data mining, which means that if you throw a lot of features on the dataset at the dataset, which unrelevant, unuseful features of the dataset, it's very good features of the neural network. It's very good in picking out those features that are really important for the problem. While that is true, it's still we are acting in a very low data region. For the neural network to do that, to pick the useful features, it needs to have access to a lot of data. The people who are usually saying this are not working in the low data region. They have access to unlimited amounts of data, very huge networks and stuff. So they keep saying that, but it's essential. It's important if you can clean the data and data mine it before, if you're especially working in a low data region, so that the network learns better when you don't have the noise present in the system. So this is where we develop the intuition. So there are 5 different cases that we have run in this section. So the first case, we'll get back to the first case. This is like the extremely important case. If I had a big danger board, I would put it right here. So I'll clearly explain what this thing is. And the second case where we'll have a very high learning rate, and then we'll have a very small learning rate, then we have a very deep network, then we have a very shallow network. So this is what you have to do. If you want to develop intuition on a neural network, you take it. You can use these networks in the notebook as well. You go crazy on them. You go crazy on the hyperparameters. You go crazy on the network architecture, and you develop intuition what happens after you change all of these values. So that being said, I'll go through each of these sections now. So the first thing is what we are essentially doing is the same thing. We have the MNIST data set. We are developing a neural network, not a convolutional neural network, just a deep neural network. And we are trying to predict the labels. The new thing that we have done at this point is this. So what this does is that you have training labels that are attached to each image. We just shuffle them. So essentially we are providing it with garbage. So a image with number digit 2 can be represented with a label of 0, or any of this, all sorts of combinations are going to be possible. So it doesn't have any physical meaning. The data doesn't have, or the image target pair do not have doesn't have any physical meaning. So if we take this data set and ask the neural network to learn something from the data set, and this is what should be really surprising at this point. It starts with a very low accuracy on the training data set as well as the validation data set, which is a 10%. But if you let it run it for like 100 epochs, at the end of 100 epochs, this is what you have to be really careful about. It got to an accuracy of about 90% on the training data set, and it thinks that it has learned something. The only way to make sure that it hasn't learned anything is to test it with the validation data set, which it has only 10% accuracy. That means, so if you have the same level for every point in the data set, you are going to be right 10% of the times. So that's what it's actually doing. So it hasn't learned anything. So it becomes really important to hold out some of your data set for validation purposes, so that you know whether the network has actually learned something or it's trying to trick us. So that phenomena is called garbage in, garbage out. Whenever you hear this phrase, this is what they're talking about. So the next case is where we have very uh, very high learning rate, which is 1. We usually use zero point 0.1 until now. Now that we have a learning rate of 1, so if this is the local, if this is the global minimum of the error surface, so the gradient descent is going to be shooting across all over it. So if you have a very large learning rate, it's going to overshoot, then it's going to overshoot again. So it's never going to. Most of the times, it is never going to get to the local or global minimum. So that's what you can see here. If you run the data set, and the accuracy got stuck at 20%. And if the accuracy doesn't improve with the number of epochs, your detective instinct should point you towards the learning rate. See what happens if you decrease the learning rate, if the accuracy is being improved or not. So that's the first thing that you have to check. So the next case is where we have a very small learning rate. So if you have a very small learning rate, it takes a lot of epochs for the network to converge to the global minimum. So that's what happens here. Even after 10 epochs, where we got 99% accuracy in all of the previous cases, we are still stuck at 97%. It takes a lot of amount of time. The last two cases are going to be neural networks where we have very shallow network, and then we have a very deep network. So this is the shallow network. So if you run the case, you are going to since it doesn't have the capacity to learn all the uh, uh, all the tricks of the dataset, it can only get to a 92% accuracy or a 93% accuracy. And if you have the very deep neural network, uh, so this is what happening here. So if you see the validation curve, it's going to decrease, and it's not going to decrease anymore because your learning rate is so slow and you are very close to the global minimum, and it doesn't have the momentum to go towards the global minimum. And if you have a very large or very deep neural network, so this is what is going to happen. So this can be easily understood by this. So the validation error actually decreases for the first 10 epochs, then it starts increasing, which means that the model is overfitting. So the garbage in, the garbage out phrase that I've just used, so it's trying to learn the uh, features that are not actually present in the data set. So it's just trying to remember the data points from the training data set, so that when you apply it to the validation data set, you'll know that it actually hasn't learned anything, and the validation error keeps increasing. So that's the notebook for me. I think we have like 5 minutes left. If you guys have any questions, you can post them in the chat box, or you can ask them directly. And I advise you guys to take this notebook, change the parameters, see what happens. That's the only way you're going to develop intuition. There's like, or else if you see it just from the outside, and if you try to understand it, it's going to be like black magic happening all the way. So someone who is experienced will be able to create a good enough architecture, provide good values for the hyperparameters. So the only way you could do that is by experimenting with different networks on different data sets. Do we have any questions? Sorry.
Let's call it a day, Mania.
Yeah. I don't see any questions. But if you have any questions, you're always welcome to write us an email, either me, Sergey, or anyone from our group, and we'll try our best to reply to your emails.
Sounds good. Thank
Yeah.
you for coming.
Yeah.